Okay, it should be recording.
All right. Can you share the screen?
Yes.
Okay. All right, guys. Welcome to lecture 12. Happy early Thanksgiving. Today we'll be talking about core ML. It's a new topic. We never taught this topic before, so we have Zane and Jiwan to teach the topic. Can you skip to announcement?
Wait, yeah.
So before I hand it off to them, I want to pass off some quick announcement. So A4 final submission is due tomorrow night, November 25th. Um, there won't be office hour tomorrow though, because RTAs are home for Thanksgiving. But if anybody have issue with A4 or have question, please send me an email. Send me an email and I'll try to help as much as possible. I think I can set up a Zoom office hour if you reach out. And then if you were there for the Hack Challenge kickoff, the teams have been released and you should be able to see your team on the Hack Challenge Ed discussion. There's also a link to the team matching and there's also a link to the slides. If you want to discuss about changing the team, if you're it's not if you realize that like some of the teammate that didn't show up, please reach out and we can try our best to work with you and also enjoy Thanksgiving. This is the hack challenge at discussion QR code on top, right? If you're not in the hack challenge at discussion, please scan the QR code and join. All right, I'm gonna hand it off to Zane and Juwon.
Perfect. Thank you, Jay. We appreciate that. I guess we'll start off with G1. Do you want to introduce yourself first?
Yeah, I guess, oh yeah, could you go to my slides?
Yep, wait.
Yeah, so hi guys, my name is Jiwon and I'm in iOS sub team as you guys know. And I joined app dev last semester. I'm working on Uplift right now, and I'm also a former iOS student. I was part of the, I guess, FA24 lecture and course with Peter and Bell. And you guys were talking about the hack challenge. I was actually the winner of the hack challenge, not to flex, but yeah, so you guys should work hard on it. In terms of like other things, I really enjoy like Stardew Valley. And I guess like in first semester, I broke my collarbone, which wasn't fun. So you guys should coffee chat me about that.
Okay, perfect. I guess I'm Zane. I joined app dev this semester. I'm also on the iOS team, obviously. My background is I was a competitive programmer and I was dropped on my head more than one time as a child. Some of them were my fault, some of them were my sister's fault. And I have the cutest cat ever, which is right here. And I also make decent chicken nuggets. Um, we don't have enough time for everyone to introduce themselves. I do know some of you already, and I would like to get to know all of you, but so you can like always reach out after this. But I guess we can like start right away. Before we get into core ML itself, I want to just give like a brief introduction to ML in general. And I would like, before we can start, I would like you to send in the chat a number between like 1 and 10. 1 being you've never heard of machine learning before, and 10 being you're a machine learning expert. Just like gauge everyone's like level of knowing machine learning. Perfect. You have a 6, a bunch of threes, a bunch of fives. Perfect. Sounds great. Um, okay, so I guess I can go ahead and start. So what is machine learning? Um, Basically, we have normal coding that you all of you guys do, right? So let's say like we have a function that returns a Boolean value. It returns true if a student has passed the test and returns false otherwise. And it takes in a parameter which is a grade. This is a normal function. Most of you have like definitely seen this type of function before. And it's as simple as just like returning like if grade is more than 60, return true, otherwise return false. This like evaluates to a Boolean statement, and I'm sure all of you have seen this before. Um, we can definitely make this more complex, and instead of like just having like a set cutoff, which is like 60, we can make it so that it's within like 4 standard deviations of the median, which is way more complex than just having like 60 as a cutoff. But this is something that is also very possible. And this is what we do when we know how the function exactly works. Like we set how we want the function to work, if that makes sense. But what if I want to do something completely different? What if I want to like know if an image has a cat in it or not? I guess we can try to do the same thing. We can try to do return a bunch of like if statements. So like if it has a nose, if it has fur and 4 legs and is an omnivore and has meow sounds, then it is a cat. Um, and this will classify some images as cats, but it'll also have some problems, as we can see here. A fox has a nose, has fur, has 4 legs, is an omnivore, and it does make noises akin to meowing. So this would be like by our rule, this would be a cat. And then this Sphinx cat doesn't have fur, so by our rule, this is not a cat. And then we can have something more complex like G1. And G1 kind of fits all the categories, but like what are we supposed to do in this case, right? So machine learning like deals with these types of complex situations, complex functions that you can't just like know how the function will exactly work. What it does basically, machine learning trains a model. We'll go more like in depth about the word train as well. But like, what is a model in the first place? A model is basically just a magic function that outputs the correct answer, right? So in this case, we don't have a model here, or our model is this. It's just a very bad model, right? In machine learning, you just make this model as good as possible. It'll still make mistakes. You make it as good as possible, and then you can just have it. And you don't write this function yourself, because if you could, then you can just make it yourself and just be done with it, just like how we did the grade. So it wouldn't make sense for us to use machine learning when we're grading assignments, because then like what are we learning? What are we doing? Because we know how to make the function ourselves, and making our function ourselves would be way easier, way faster, way more accurate as well. Um, so basically this is a model. You have input, it goes into some magic function and it gives you an answer, right? Now, let's go more in depth about how to make this magic function or how to make this model. Training is basically when you show the computer a lot of examples with answers until the computer basically learns what the answer should be for other examples. Um, and as an example, I have here like you give it 10,000 images labeled cat or not cat, and the model adjusts itself again and again until it can guess the right answer most of the time. So this adjustment of the model itself is called the learning algorithm. And there's so many different learning algorithms. It's a really like interesting field, and I suggest you guys like dive deep into it if that's one of your interests. But does this make sense to everyone? If there's any question at any point, you can just like raise hands or type in the chat and I'll see it. Um, but yeah, basically we train just like how a baby like learns how to say stuff. Like you keep showing it an image of something and calling it that something's name, and at the end the baby will be able to like correctly identify it. This is the same thing that happens with machine learning. Now, I want to give like a brief demo about some different learning algorithms. So here we have the k nearest neighbors, or basically KNN. And I'm gonna make this like a lot simpler. So we have two classes, right? Let's say that the blue class, like this point right here, let's say that this is an input, right? This is a training input that happens. And this point right here is classified as blue, which is in this case positive. So if we're going back to the example with the cats, this input would be a cat, and this input would be not a cat. Blue inputs are cats, red inputs are not cats. Does that make sense? Perfect. So how this algorithm works is the model itself is just all of these points, the training points, right? And whenever we want to add a new point, we just look at where it lies. So let's say like I add a new point and it lies here. I would note that this is not a cat because it lies in the red section of this graph, right? And if it lies here, then it would be a cat because it lies in the blue section. But how do I even draw these boundaries? As you can see here, there's like number of neighbors right here that you can change. And basically what happens is at any new point, let's say like I add a point right here, it looks at the k nearest neighbors. Right now k is set to 1, so it looks at the nearest neighbor and it checks what the nearest neighbor is. The nearest neighbor here is blue, as this is the point that would be the nearest. So this would be classified as blue, which is why this whole area is blue. Same thing here. This is closest to a red point, so this is red. And as you can see here on the border, this means that the distance between it and the closest blue and it and the closest red is the exact same. So it's like it wouldn't know if you have like a point exactly on the border. Now, if we change k, right, we can see something different happen. This means that instead of looking at the k nearest neighbor or like the only one nearest neighbor, I'm looking at the two nearest neighbors. And I'm checking if the two are red, then it's red. If the two are blue, then it's blue. But if one of them is red and one of them are blue, is blue, then it's a tie and it's basically nothing, which is what the white is, right? So you can see that this only happens in the even cases, which I kind of see as like it's kind of self-explanatory because if you have odd cases, there's never going to be ties. But basically, let's like for this is the same thing, but it looks at three nearest neighbors. As you can see, I set k to 3. But if we go back to the nearest neighbor, you can see if I change one of the points, how the graph changes, right? Right now the graph changed because this point is now closest to this instead of this, right? When I had this here, it was closest to this, but I can change this and you can see exactly how it changes. Now setting k really matters here because let's say that you have this kind of graph, right? And let's call this an outlier point. So like this would be like something that doesn't look like a cat at all, but it is actually a cat. For example, like it would be the Sphinx cat in our case. And this would be a cat, right? But for the k-nearest neighbors now, everything in this area is also a cat because of this one point. And this shows like how one outlier can basically change a lot if k is equal to 1. Now, let's say k is equal to 2. You can see that this is basically all white now. If we set it to 3, we can see that this point doesn't even play any role in anything. And this is kind of what it should be because it's like an outlier. Um, and you can set k to many different values, and every kind of like different problem has like an optimal k value, which I guess you can figure out by trial and error. Um, and yeah, it's just basically like this idea of the intuition is you find a way to represent the data. In this case, we represent them as 2D points on a graph. And basically the intuition is I am what I'm closest to, right? So we can say like we can do this easily if we say like the x-axis is the height of the dad, the y-axis is the height of the mom, and then like you're blue if you are projected to be like higher, like taller than 6 foot, and you're red if you're projected to be shorter than 6 foot, right? So this would be an easy way to represent that type of data because it would be just 2D and it would be simple. Um, and you can easily do this. Now you don't have to do this with only 2D data inputs. It could be 3D, it could be 4D, it could be 12D. It doesn't really matter. And we don't have to think about them as dimensions. We can think about them as just like basically what is called a feature vector. Um, and it's just like a bunch of numbers that describe what the thing is. So we can have like a million features, like the location of the house, basically like the longitude and latitude line, maybe like the weather in the area, maybe how expensive the house was when it was bought, maybe the year. We can have like a bunch of different features that describe this house, and then we use these features to figure out like how much you should pay for the house or something, right? Um, and that's basically like how this works. So what is the model in this case? We have to store every single one of the training points, right? Because whenever we have a new point, we need to compare it to the k nearest neighbors, like see the nearest neighbors for this point, and then see how many of them are red, how many of them are blue, and then we decide what color our new point will be, right? So our model is all of this training data. And all of this training data means that we are keeping track of every single point, every feature vector for every point. So for these points, it would be an X and a Y. And we're also keeping track of their labels, right? And then when we get a new point, we can just compare it to the k nearest neighbors. For example, like 3 nearest neighbors, and then like figure out, like predict, like, oh, this point we think it should be red, or this point should be blue, right? Um, so the model in this case is the set of all the points, all the training points with their labels. Now I guess I'll go into the perceptron algorithm, which is more like what you think machine learning is, right? So let me show this case. Basically, what the perceptron algorithm tries to do is it tries to separate the points with a line, and it separates the points into blue points and red points. Basically, everything on the right of this line should be blue, and everything on the left of this line should be red, for example, right? And this algorithm was actually made in Cornell. And if you take ML 3780, you will have to learn more about this. But basically, the way this algorithm works is it's initializes this line as the line that goes through 0, 0, and 1, 1. So x equals y. And then at every point, it looks at every misclassified point. And if it finds any misclassified point, it changes, like it rotates the line a little bit and it changes its position a little bit so that this new point will be classified correctly, right? So let's say like this is the training data that we have. And this is the line that we start with, goes through 0, 0, and 1, 1. And what we're trying to do right now is we will see for every misclassified point, we will do something that will change how this line is right now. So it'll change the rotation, it'll change the position. And in each step, it'll get closer to actually separating the data, right? So we can see here, I can press like step, and you can see it choose a line, choose a data point that's misclassified. So it shows this data point right now. And then if I step again, you see the line change. And then again, it chooses another data point. So this is misclassified. It changes. It keeps doing this, and it keeps changing a little bit by a little, a little by a little, until there's no more misclassified points, right? And this is what my intuition says about learning. Like it's actually learning. It's trying to fit to the data. It's seeing the data and it's figuring out like, oh, I made a mistake. Let me actually fix myself, right? So this is what actual learning looks like. And at the end, if I just play this and it goes faster, you'll see how it keeps moving a little bit at a time. And then at the end, it'll exactly go through a place where it like separates the data. So as you can see, the blue points are above this line and the red points are under this line, right? Now, what is the model in this case? So after I train this line, the model is just this line alone. Basically, the model is the thing that you use to figure out the label of new points. So how would I figure out if this point right here is blue? I would just look at the line and I would see that, oh, this blue point, like this new point is above the line, so it must be blue. And this point right here is below the line, so it must be red. And that's basically how it works. So this model is basically just the line itself. And as we all know, a line equation is given by like the equation ax plus b equals y. So basically, we only have two variables for this model, and that's everything that we need, right? Um, but I'm sure you can see like this is not a really smart algorithm. This is kind of dumb. Like, what if there's no way to separate the data? What if our data is in 3D instead of 2D? What if like something else happens? Like how would we fix this? And as you can see here, there's a line right here that says generate linearly separable data. And what that means is data that can be separated with a line. So if I turn that off and I restart, as you can see, like we have a blue here, we have a red here. And like you can try, but there's no line that you can draw that will separate this data perfectly, right? So this algorithm will just run forever because there is no like stopping point. There's no place where there's no misclassified points, as you can see here with the while loop. And this is like one of the problems with this algorithm. It's a very simple algorithm, and it gives you a model that can be basically just two variables, like an x and a y, or like an a and a b. So it's very lightweight, but it's also dumb, right? Um, And there has been like a lot of improvements on this model. Like there's perceptron models that allow mistakes, and they have margins and a lot of stuff like that. And there is a different way to have it like go into a higher dimension. Um, but it doesn't like that. That's not really what we care about right here. I just care about like the training process itself, right? So at each point, it's just like fixing itself a little bit. With the k-nearest neighbors algorithm, there is literally like no training because it's just like stores all the data, all the training points. But yeah, like this will go forever and ever. And if we go back here, this is like a simple comparison. So the k-nearest neighbors algorithm does not learn; it just stores the data. The perceptron, it adjusts its weight until classes are separated. And then the prediction style for the KNN is it just like for every new point, it looks at the nearest points and it figures out like is this like from the nearest points, from the K nearest points, how many of them are red, how many of them are blue, and then it figures out itself. For this one, it just takes the line and compares like the position of this new point to the line. And then the intuition is like, oh, just ask your neighbors here and then like move the line until mistakes stop. Does that make sense? Do you have any questions about these two algorithms? Perfect. Again, like I don't expect you guys to like know or memorize all of this. Like this does not really matter. It's just intuition on how a machine learning model actually works, how to make your machine learning model, and some algorithms that can help you do that and achieve that. Um, so again, how to make your magic function. There are many different algorithms, many different model types. You don't have to know about them. There's supervised and unsupervised learning. There's deterministic models. There's generative models. A lot of things. Um, Basically, what I want to say as well is that any function has parameters, and you have to choose the best ones for your model. So remember when we were talking about the representation for something? Like you can represent a house with a vector of like 1 million adjectives, right? Basically, you have to choose adjectives that actually make sense. Like if I'm looking at gym occupancy for at Cornell, for example, I'm not gonna like have one of the feature models be like the stock price of Nvidia, right? Like it doesn't make sense. There's probably not gonna be any overlap between these two things. Maybe there is, but there's probably isn't any. So I have to choose feature features that actually make sense. So the features that I would choose for like a gym occupancy is like the date. So is it a Sunday? Is it a Monday? Is it a Tuesday? What day is it? What gym specifically is it? Is it like Helen Newman? Is it Morrison? Things like that. What the weather was at that day. Was it like really raining? Was it really snowy? Was there a blizzard in that day? Um, and other stuff like that. Like maybe is it a prelim night or is it a holiday? Stuff like that. But I wouldn't just go and like be like, oh, like take into account the price of an egg in that specific time and date, right? Because that wouldn't make sense. So you have to choose a way to represent your data. And then once you do that, you can choose an algorithm and a model type to create a model. So it could be a k-nearest neighbors model, it could be a perceptron model, it could be a tree regressor, it could be a random forest. Like there's a lot of different names. And I suggest you guys like read a little bit about at least like the intuition behind each of them because it is really interesting. And if you plan on going into ML, it's gonna be helpful. But simply put, you get tons of data, you put them into some representation, then you use some algorithm, and then you figure out like exactly what the model is, and you get a model. And every model has this one feature where you can input in a new like unlearned point, and it will predict what the point label will be, right? And that's basically how to make a magic function or how to make a model. The other way to make models is to download them from the internet. And this is like a perfect segue into Core ML because Core ML doesn't actually make models itself. It just teaches you how to use a model downloaded from the internet or made from another library. And I guess G1 can take over.
Yeah, so I'm gonna give you guys a link. Yeah, so if you guys go to that link, you guys can download the CSV file and the GitHub repo, which has the boilerplate of the code that I'm gonna work with. Basically, we're going to create a model in with create ML functionality in Swift, and also the core ML, and actually use that model. So yeah, I'm gonna give you guys some time to download the CSV and clone the repo. Yeah, let me actually share my entire screen. Yeah. Mhm. Yeah, so if you guys like forgot about the cloning command, just go to the folder that you want, like documents, and then just do git clone, and then you guys should have the SSH link, and then just copy that, and then just clone it, and then just open the Xcode project file, and that should do it. So yeah, did you guys have it downloaded now? I'm I'm gonna assume that you guys have it downloaded. Okay, yeah. So yeah. So first of all, we're gonna be working with create ML, and this functionality is in Xcode, and then open developer tools, and then there's also a functionality for create ML. And then for this, we're going to create a new document, and then we're going to choose a template. And this is the template that Zane was talking about. Like you can have like different things. You can have hand pose classification, which is kind of funny. Text classification, even sound classification, um, image classification, which could be used for like cat and stuff like that. For our purposes, we're gonna be using tabular regression, and I'm going to explain why. This is because we downloaded a CSV file, and this CSV file is basically made in tables. And tabular regression basically utilize that tabular functionality or like table functionality to create some output. And even though our CSV file might be pretty small, um, the CSV file you can actually like download them from like for example like Kaggle. Kaggle is like a data science kind of like competition website where you can download like different like data sets, and from there you can like train different different models basically using your CSV files. Um, I highly recommend you guys check out Kaggle and download like data sets that you guys want. There's like really interesting data sets such as like Uber data sets, like dog versus cat. But for now, we're just gonna be using a CSV file, and this is the better res CSV file. And if I actually open it, this basically has four tables with four columns, and basically has wake, estimated sleep, coffee, and actual sleep. And basically, this is actual sleep is going to be our output. We're going to get the I guess like ideal wake time, which is like this in seconds. Estimated sleep, which is how many hours of sleep we want, and coffee intake, like four cups of coffee or something like that. And it's gonna output a I guess like ideal sleep time. And basically, we're just gonna feed this into this model called tabular regression. And after we do tabular regression, we can name it anything we want. I'm just gonna name it better sleep because better rest because it's gonna make me rest better, I guess. And then we can just save it. I'll just save it at download. Yeah. And now it's gonna give you a pretty intuitive UI. You can feed in training data and then validation data, which is something else that you can do. But for now, I'm just gonna focus on the training data. Like Zane mentioned, the training data is just the data that you feed in, which could be part of the model. But actually interesting is that Swift doesn't actually consider the training data as the complete model. It just considers considers the prediction as the model, which is something that's different. But select and then choose the CSV file that you want to feed into. This is our data set for like abstractions. Uh, and then basically now we have the training data and we want to like actually choose the target or like the output that we want to have. And from here, we can see that we have wake, estimated sleep, and coffee and actual sleep. And if you remember from what I was talking about, our output is actual sleep because we want the values from wake, estimated sleep, and coffee, and then output it into something that we can actually use, which is actual sleep. So be sure to choose actual sleep. For choose features, I don't think we have to do anything for this. For algorithm, these are like the different algorithms that you can use. And Swift is actually pretty smart for this. You can see that it has like some kind of like algorithm that Zane mentioned. But if you do automatic, it's just going to analyze your data set and then basically choose the best one to use. So you don't have to actually worry about which algorithm you have to use. If for people who are like actually like deep into ML and stuff like that, you're gonna have to choose like you're gonna have to actually like configure these stuff based on the data. But for now, automatic is fine. And let me see. Training data. Oh, oh yeah. So I guess like yeah, I forgot this part. But for choose features, make sure you choose all the features. And I think this is where it actually like sees that oh you chose these features, so we're gonna load those data sets. And then we can actually see that our data set isn't that large. It only has like 10,000 items, but just for demo purposes, it should be fine. And now we have everything that we need. You can add validation data, testing data for something like that. But for something simple as this, I think this should be enough. So now we just click the train button and then it trained successfully. This would take longer if our data set is larger, and usually it is larger, like insane amounts of like data sets, like gigabytes of data sets, but just for demo purposes, like I said. So now we trained it, and we can actually see the results. You can see that the automation algorithm actually took like some part of the training data and used it as like a validation. And this Zane kind of mentioned this, but basically what our model does is that we can't use all the data set as like training the actual data. We want to actually like validate our data, and that's where our validation comes in. So I'm not like a data scientist, and I don't plan to be a data scientist, but I guess like good practice to have if you have like a data set is to use like 10 to 20%. I'm not sure the actual numbers as like a validation data set. You might have heard of this before, but use like 80% of your actual data using to actually train the data and then use the remaining to validate the data. And so that's what Swift actually did, or Create ML actually did. They used like some validation data to actually validate if our data set was actually working and our prediction was actually working. And then you can see the maximum error, root mean square error. This is just the error points. And then there's also like a testing section. You don't have to worry too much about this, but testing is just like testing is the part I heard that was like really fun. I'm not too sure about like how to like configure testing, but basically after you create the algorithm or like create the model, you want to actually test it with different like circumstances to see how perfect our data set is. So you like often hear about different people saying like, oh, my model is like 95% perfect or something like that. It's like 90% perfect. So that's basically like from testing. You test some data and then basically the model basically like spits out a value and then you basically say, oh, that's like correct or not correct. But we don't have any testing data, so we're gonna skip this for now. But this is usually the like very important step in the like model creation. So yeah, so now we have the actual output with some metadata. we can see that the input takes like a double estimated sleep and coffee, and then takes like output with actual sleep. And now we can just do get better rest and then just save it in our downloads folder. And this would download our model. So yeah, just to talk about like the size, the reason why it's like 534 bytes is because like I said before, like this model doesn't actually save the data points. It only saves like the prediction that you have. You can add more like training data and more like validation data or like testing data later when you create the model. But the reason why it's only like very small, which is kind of surprising, is because it only like saves like the estimation or like the actual like algorithm into predicting the actual sleep output from the inputs. So this 534 bytes is actually just made up of all of just like metadata and then just the prediction data. So anyone have like a question or like any like, I guess, technical mishaps, or is everyone following? So yeah. Okay, perfect. So let me just go ahead. So if you've done this correctly, you should get something in downloads called Better Rest ML model. I don't think this is necessary. Actually, is it? Oh, it's just a project file. But this is the important one, the ML model. So if you have that, then you're set for the next step. So yeah. So if you guys actually like clone the repo, you can actually see like a boilerplate for like better rest. And it just takes like a simple input, like when you want to wake up, desired amount of sleep, and then coffee intake. And these three inputs are similar to the inputs that we defined in the CSV. Um, yeah. Also, like, let me know if you guys are having trouble with like downloading the files and like cloning the repo. But basically, I guess like Jay and Asin went over this, but we have like stuff here, and then I guess like these are just like SwiftUI stuff. And what we want to do is that we want to give an alert if on the the estimated sleep or like the ideal bedtime to the user. So we have the state variables and then I guess the actual like UI code. So the first thing we do is import core ML. Make sure you guys have this because this is the library that we're going to use. So that was create ML, and now we're actually going to use the library, which actually imports the model that we created. And this is core ML. So make sure you guys have core ML. So now we want to use the ML model, and to do this, we just drag it into our folder, and then this should create I guess, a class, a model class. We can't actually do anything about this file other than just like to import this called better rest. And just for like, I guess like better naming um, conventions, I'm gonna name it sleep calculator. So this is So now the class is auto-generated. Swift does this a lot. If you actually work with like GraphQL and stuff like that, there's a lot of like auto-generated files in that. But basically now, based on the models, it's gonna create a sleep calculator. Um, and then you can see all the information. And the author should be your guys' name, by the way. So now we actually imported the sleep calculator class. And we want to actually use the inputs from the UI and give out a certain output using the model. And sorry about that. Like Zane mentioned, we don't want like a function for this because of the fact that like this is based on like human data. There's so many like variables and like so many like outliers that we want like a model. And that's why we use a model. So if you go to line 64 to 69 and see the calculate bedtime. I think it should be like a to do or whatever. We're gonna finish this function. And this function basically just calculates the bedtime using the model. So the Zane mentioned like, oh, like this could be like a image classification of like cats, but we don't want that, right? So we use like a for now, we're gonna use the same function, but we're gonna use this function to utilize the model that we just created. And this function is called from where is it called from? Oh, here. Yeah. So there's gonna be this button calculates um, activates this calculate bedtime function, and we're gonna give out a alert. So the first thing we do is that there is a possibility that our model will spit out an error. And you guys have heard of, I'm sure of like try catch blocks. So we first set up a try catch block because our model will sometimes will give errors and we want to catch it with a try catch block. And in our try block or do block in Swift, we first define the ML model or configuration. And to do this, we just do let config equals ML model configuration. And basically, this configuration class, you don't have to know deep into this, but it's just a class to like configure like different settings for your model. Like if you want to use CPU or if you want to use GPU, something like that, you can configure using this. But we don't actually have to use this in our app because we're not going to configure anything. But this is for like you guys to play around if you guys want to optimize your models for like better performance, for example. And now we actually define the model, let model, and then this is where the try catch block is good. Um, so we do try, and then this, so Swift autocomplete is actually wrong here. It's sleep calculator because we renamed it. And then our configuration is just the config that we defined. So now we have the configuration and the model setup. So now we're gonna actually define the inputs from our user as the inputs for the model. So if you remember, the inputs that we defined are um, wake double, estimated sleep double, and coffee double. So we somehow have to convert this date. So this is fine. And coffee amount is easy, so we can just make this a double. But wake up time is actually a date object. So we somehow have to convert this date object into a double. And to do this, we have to first define the components of the data object that we want. And for this, we just want the hour and the minute because we want to convert it into seconds. So calendar dot current dot date components. And then actually I don't want that. And then this will essentially just give you the components that we want, which is minutes and hour. And yeah. And then inside this brackets, we can define the components that we want. I'm not sure why this is not getting highlighted. Um, Let me actually finish this. And then we want it from wake up state. So yeah. So this will essentially just pick out the components. You don't have to know too deep into this, the hour and the minutes. And then we want to convert the hour and the minutes into seconds. So all we do is just get the components dot hour nil coalescing 0 times 60 times 60. And then for minute, it's the same thing. You get components dot minute nil coalescing 0 times 60. And this will essentially just convert it to hour and minute. And the reason why the nil coalescing is because of the fact that like there could be stuff there and there could be not. And if there isn't, we know for sure that there is stuff there, but there isn't, we want to just default to 0. And now we have the wake up time. Now we handle the wake up time. So we can simply just put in all these values into our model. So now we're going to define the actual prediction. And this is the try catch block. try model dot prediction, and then it takes in wake estimated is sleep. Yeah, I think so. Coffee. Yeah, that's right. Then wake takes up the the double of hour plus minute that we defined. Estimated sleep just takes in the sleep amount. We don't have to change anything for this. The coffee takes in a double value of the coffee amount. So these are the inputs that we need, and we define that. And then this will, as you guys remember, this will just like our model will just give out the sleep amount, the ideal sleep amount that we need. And that's not what we really want to the user. That's not good interface. If you just say like, oh, you need like 9 hours of sleep, like the user cannot form oh yeah, yeah. So let me just like we're almost done, so it should be fine. Um so basically, you just need to like we need to somehow convert that data into the sleeping time that we want. So what we do is that we do let sleep time is equal to wake up minus prediction dot actual sleep, and this will actually give us the sleeping time for the user. And I actually spelled this wrong. So, yeah. And then we're gonna define the alert title. I'm just gonna speed through this. This is just defining the title of the alert, and the alert message is equal to the sleep time. uh, And all this does is just change the sleep time that we define into a date format, date block again, or date object. And catch is just, we just want to give out a alert, like error, alert message. This should be fine because I know for sure our thing won't break. So now we just after doing all this, we show the alert, and then this should be it for everything. And just refresh. So now we can click calculate, and based on our inputs, it's going to give out a output called 10:38 p.m. Let's see. Yeah. So what if we change values? I want to wake up at 6 p.m. because I'm kind of weird. Um, I want to sleep 14 hours. Oh, I can't do that. But daily coffee intake, I don't know, 4 cups. So what if I have a diabolical sleep schedule like this? Your ideal bedtime is 4:56. So yeah, now, yeah, if you try different outputs, um, for 11 a.m., you can like play around with this. This is just basically from the model that we created. And yeah, so yeah, and so you can see that it's working out pretty well. Uh, yeah. So yeah, let me know if you guys have any questions for this. Alright, perfect. I'll then that's it for me. I'll hand it back to Jay, I guess, for I don't know, to send you guys off.
You guys are good to go. Thanks for coming to lecture for, to all of you for the day before Thanksgiving break. So I already took all my lectures except for this one. Uh, but yeah, thank you guys. Happy Thanksgiving break. Oh, if you have any question um about the hack challenge or for A4, stay back. And if you want an office hour for A4, stay back. We can set it up together right now. Yeah, thank you, G1 and Zane. It was great. Great lecture.